Here's the lab notebook for energy conservation with the spring. This is where we define the variables that are in the table. This is a two-part table, by the way, so don't think you only need the top part or the bottom part. This is all one table. We have the H0, that's if the spring is hanging with no weight attached. That's with no stretch at all. It's either no weight attached or you're holding the weight in your hand. H1 is going to be around halfway down after you let it go. That's going to be the height when you have the maximum velocity, which we saw in the video earlier. H2 is the bottom height. It's when the Y value is the biggest, so it's the maximum stretch. So if you really were able to catch that on your data, that would be, your velocity would be 0. Now it may be that your camera, because it's going every 30th of a second, that the bottom is hit in between two pictures, so you may not be able to catch exactly where the velocity is 0. The formulas we're using are the force of the spring is K delta X, that's Hooke's law, which we should know, and I did not show you how to do it, but from our Hooke's law lab you should know how to find K from that. I'll show you down below where I did that. You have the potential of gravity, which we label UG, and we have UG0 would be the potential here, UG1 here, UG2 here, and we use that notation for everything. We've already talked about our HOs and H1s. Same thing, the 0 is always all the data that belongs here. The potential energy of a spring, which I label US, is 1/2 K, the spring constant, times the distance you stretch squared, which in this case will be my H's, because this is no stretch, so my distance for 1 would be H1, and I didn't put a separate entry for that in the table. The kinetic energy is 1/2 mv squared. And your total energy is the potential energy plus of the gravity and the spring and kinetic energy. And unless you have an outside force interfere other than gravity, gravity and the force of the spring are called conserving forces. In this situation, if we could measure it perfectly, this total energy would never change. Now you have an option of how you define what your potential energy is, but once you pick a reference point, an origin, then this total will never change. So let's look at how I actually did this lab. First thing I did is I hung the weight on there and just let it sit there, and I measured the distance it went, which in my case was 16.5 centimeters was my stretch, or 0.165, and I hung 1/2 kilogram. And I recommend, because there's not a lot of weights on this, that you actually weigh the weight to be as accurate as possible. Mine turned out to be exactly 1/2 kilogram. So notice this is the force and not the mass. This is 4.9 newtons. So that was my spring constant. Then my potential gravity was mgh1. I didn't bother figuring it for H0 because for H0 it's going to be 0. And again, I entered my spring constant here. So these are measured values. The H's and the V's are measured. So I have 0, and I measured this off the table like I showed you in the video earlier, off the table, and my velocity values were measured. These are all 0. Everything's 0 at the beginning because we're not moving, so I have no kinetic energy. The spring isn't stretched, so there's no potential, and we're defining our starting point as 0, which means as I go down, my potential energy is going to be negative. So I plug in mgh, and I use 9.8 to get more accurate data, and I put in the number that I measured from here, and that's my potential energy for gravity. My spring, I use the same delta X, only it gets squared, and there's my spring constant. I use this formula, and that goes here. My kinetic energy, this is the one time I have data for all three. I have 1/2 my mass times my velocity, which I read off my table in my graphical analysis. I get this. When I add all three of those together, add them algebraically, so I have a negative added to a positive, I get a negative 0.08. And I'll show you how. Then we're going to take that and divide by the potential energy to do a percentage difference. This really should be 0, so I can't compare it to 0 because if you divide by 0 you get infinity. So the best we can do is compare this, just see how big this value is compared to the potential energy that we have. Then it took me more than one page. I did this. I added them. This is where I added all three of them together. My potential, and kinetic. I add them together. I got my negative 0.08. The potential difference is just the total energy divided by the potential gravitational energy. And I got 8.8%. The biggest error I suspect is in the velocity, because it's really hard. I suspect if I did the exact same video and did the dots, I get different values for my velocity, because it's hard to pinpoint exactly the same spot on the mass every time. And then this is just doing the same thing. I don't need to walk through that. And the second time I got 4.1% error. So I'm getting less, as a percentage basis, I'm getting less error as I go along. Although this was negative and this was positive, so I went from being below to above. And then the spring, so it didn't really stay exactly the same. So anyway, that's how you do the lab. And again, the main purpose of this lab is to show you, again, in real life data, it's always hard to get it exactly, but theoretically, this total energy here will equal the total energy here, which equal the total energy here. And with a spring, when the weight's just dropped, the only energy that you have to worry about are the potential energy of gravity, the spring, and the kinetic energy. The sum of those three will always remain the same. And that's a very important scientific concept called energy conservation. Good luck.